we have started discussing about the preparation of alkenes from alcohols. So, we have studied about the preparation of alkenes from alcohols by Al2O3. Now, we will discuss about the second type, dehydration by mineral acids. Okay. So, again let us take ethanol. When we treat ethanol with concentrated H2SO4 and heat, we get ethene. Okay. So, this is the reaction. Now, reaction mechanism. So, H2SO4 is a strong acid, so it will dissociate as H plus and HSO4 minus. Okay. Now, this is ethanol. There is H plus. Now, there are lone pairs of oxygen. Lone pairs of oxygen will take up H plus and it is formed like this, OH2, that is water, and one positive charge will be on oxygen. Why positive charge? Because it has given these electrons to H plus and formed the bond. Okay. Now, since water molecule is a very good leaving group, because positive charge on oxygen is unstable. Okay. Oxygen is a very electronegative element, so positive charge on oxygen makes it unstable. So, this will try to get back electrons and neutralize. So, it will take this bonded electrons with it and water molecule will be eliminated. Now, if oxygen takes this bonded electrons, so the positive charge will be transferred on carbon. Okay. So, positive charge is transferred on carbon. Now, there is HSO4 minus in the system. So, HSO4 minus will take this hydrogen, this bond will break and the electrons will come here and form a pi bond. So, ethene molecule is formed. So, this is the reaction mechanism for dehydration of alcohols by concentrated H2SO4. Okay. So, we had discussed that the reactivity of E1 reaction, right? Why E1 reaction? How is this reaction mechanism? It is going through the formation of carbocation. So, this is E1 reaction. So, reactivity of E1 reaction was tertiary greater than secondary greater than primary. So, for primary alcohols, need concentrated H2SO4, okay. But secondary and tertiary alcohols may react in presence of dilute acid, that is dilute sulfuric acid also. Okay. So, this was the method for preparation of alkenes from alcohols. Now, there is a very important factor here. So, let us say if this is the alcohol and we treat with concentrated H2SO4. Okay. So, now what will happen? So, there are 3 hydrogen. This is 1,2 elimination, right? That is beta elimination. Why? Because this is the alcohol group. With respect to the alcohol group, this carbon is alpha and the carbon adjacent to this carbon will be beta. So, in this case, there are 2 beta carbons. So, one carbon is having 3 hydrogen and this carbon is having 1 hydrogen. So, now if in the first step this is the carbocation. Now, if some of these hydrogens are taken up by HSO4 minus, then this alkene will be formed, right. Now, how is this alkene? It is like this. There are 2 hydrogen and one is this alkyl group, let us say R, and one is this hydrogen. Okay. Now, if this hydrogen is taken up by HSO4 minus, then this alkene will be formed. Now, this alkene is like this, CH3H and let us say, okay. So, this is one alkene and this is one alkene. Okay. Now, which one will be the major product here? In this case, stereoselectivity does not occur. In this case, the phenomenon that occurs is called regioselectivity. Okay. Now, stereoselectivity was the phenomenon in which one stereoisomer of the product was formed more than the other stereoisomer. That is, one stereoisomer was favored. That was called stereoselectivity. Now, what is regioselectivity? That is, if the bond formation can happen in 2 different regions of the molecule and one region is favored over the other region, then that is called regioselectivity. Okay. In this case, in one case the double bond was being formed between these 2 carbons and in another case the bond is between these 2 carbons. Okay. So, the region of the double bond formation has changed. So, here rises a term that is regioselectivity. So, it can be written as breaking or making of bond in one region of the molecule preferentially over the other region. Okay. This is called regioselectivity. Now, the formation of alkenes are governed by a rule called the SATHEE rule. Okay. What does the SATHEE rule says? SATHEE rule says that the alkene containing maximum number of alkyl groups on the double bonded carbon atoms is favored. Okay. That is, the alkene containing maximum number of alkyl groups on the double bonded carbon atom is favored. In the last lectures, we have discussed about why the stability of more substituted alkenes are greater due to hyperconjugation, right? For the same reason, let us say if this is the double bond and there is one substitution, and in another case there is two substitution, then this will be favored. Okay? Then this will be the major product. So, similarly in our case, these were the two products. In this product, what was happening? There were 3 hydrogens and 1 alkyl group, and in this case there is only 1 hydrogen and 3 alkyl groups, right? So, this alkene will be favored. So, in this case the major product will be this will be the major product and this will be the minor product. Okay. So, this is the regioselectivity and this is called the SATHEE rule. SATHEE rule also has some exceptions, that is, in specific molecules SATHEE rule will not work. There is another rule called Hoffman rule also, but we will not go there right now. Okay. So, before starting alkyl halides, there is one last method left from alkenes. Okay. So, for the preparation of alkenes from alcohols, we had read about these two methods. One was from Al2O3, another was by H2SO4, okay, by sulfuric acid, and the third method is by phosphoric acid, that is H3PO4. This is generally used for cyclic alcohols. Okay. So, let us say this is a cyclic alcohol. Okay. We give H3PO4 and heat. So, this will be the alkene formed. So, it also follows the same mechanism. H3PO4 is like this. Okay. So, one of this hydrogen is taken by the lone pair of oxygen, then there are beta hydrogens present. It will be like this, and H2PO4 minus is formed. This will take up the beta hydrogen and alkene will be formed as usual. It is the same mechanism. It is mostly used for cyclic alcohols. Now, if we take this compound and treat with H3PO4 heat. There are two possibilities. One can be this, because beta hydrogens are present here, and another can be this, because one beta hydrogen is present here also. Now, according to the Setzeff rule, this is more substituted because this has one hydrogen and three substitutions, whereas in this case there were two substitutions and two hydrogen. So, this will be the major product and this will be the minor product. Okay. Now, we will start about the preparation of alkenes from alkyl halides. Okay. So, alkyl halides are like this: X, okay. X can be chlorine, bromine or iodine. Fluorine is not applicable here, only chlorine, bromine and iodine, okay. If we treat this with alcoholic KOH or alcoholic NaOH, this is a very important factor, okay. Not aqueous. What is aqueous? If we say aqueous KOH, what will this means? It will mean that potassium hydroxide dissolved in water. This will be aqueous KOH. If we say alcoholic KOH, that will mean potassium hydroxide dissolved in alcohol. It can be ethanol also, okay. So, this is alcoholic KOH or alcoholic NaOH can be used, and it will result in the elimination of HX, that is halogen acid. What is HX? It can be HCl, HBr, HI, etc. With the elimination of HX, it will form alkenes, okay. So, this mechanism is known as dehydrohalogenation. Dehydrohalogenation. Why? Because one hydrogen and one halogen are being eliminated. This is why in the when we were preparing from alcohol, we were saying dehydration, because water molecule was being eliminated. Here one hydrogen and one halogen are being eliminated. So, this is called dehydrohalogenation. So, this is also beta elimination, okay. But in this case it is E2 mechanism. When we were preparing alkenes from alcohols, we were having E1 mechanism, but in this case the mechanism is E2. So, this is R, okay. If let us say this is, if this is the reactant and we treat this with alcoholic KOH and heat, so what will happen? KOH is base, so OH minus will take up this hydrogen this bond will break and this will be liberated, that is hydrobromic acid is being liberated and propene is formed. Okay. So, this is the mechanism of dehydrohalogenation. We will study in details about dehydrohalogenation and we will discuss further into alkenes in the next lecture. Thank you.